This video is going to take you through chapter 1, sections 1 through 3. So this is the beginning of the course and this is the beginning of the chapter. A lot of what you're going to see in this video is vocab based. So it's important to just learn some of the terminology, and then of course there's some application. So chapter 1, section 1 is called Points, Lines, and Planes. 3 very important things to geometry, the foundation of geometry, and again, just some vocab terminology first. So we start with a point. A point, by definition, is a single dot. It's the simplest figure in geometry. We name it with a capital letter. So when you see just the letter A or just the letter B, those represent points. You can also see it written with the actual word point in front of it. So it would say point A or point B. When it's drawn in space, it will have that little dot. So that's what it means by the single dot. And then the letter would be next to it. All geometric figures consist of points. So they are all made up by some points. And again, specific amount will change, but they are all made up from points. Next up is a line, and by definition, a line is a geometric figure consisting of at least 2 points. So it obviously is more than just 2, but at minimum is 2 points. It extends in 2 directions, and it doesn't end. And that's important because that means what these arrows are doing at the end is continuing on in each direction. Because it doesn't end, it cannot be measured. So you can't find the length of a line. A line is named by 2 points or a single lowercase letter. So this line that's drawn down here can be called line AB, and it would be the word line with AB after, or the line symbol with both arrows over the letters AB. And order is not important there, so it could have also been BA with the line over it. Or this smaller italicized letter off to the left, which is an L in this case, can also be used as its name, and so we could call this line L. Through any 2 points, there's exactly 1 line, and that means if I draw 2 points, you can only make 1 line that passes through that. You can't make any more than that, and you can't make any less than that. So there is exactly 1 line through any 2 points. Next up is a plane, and a plane, or a geometric plane specifically, is suggested by the floor, wall, or tabletop, all rectangular or parallelogram shaped objects. A plane extends without ending, so although we might use a rectangular shaped drawing to represent a plane, these would in fact actually be lines that never end, which means they would expand on in all directions. So if you could picture like the floor in a classroom, what's inside the classroom could be a plane, but it also would extend outside the walls of that classroom and again, not end. It also has no thickness. So while there might be length or width, there's no height to a plane. And although it has no edges, it is shown like the figure below. So like we just said, this is what it would look like. And although those look like line segments, they would actually continue on in all directions. You can name a plane by a single letter, single capital letter, or by 3 or more points it contains. So if you look at this plane, for example, you can either call this plane M, or if there were coordinate points like A, B, C, you could also call it plane ABC, or BCA, or CAB. The order of the letters is not important there. What you can't do is mix M in there. M is not a point. M is the actual name of the plane, so you can't use it as a point. If it had a dot next to it, now I would say that that's a point, and I can't use it by itself anymore in its name. I can call this ABM or MBC, something like that. But again, without that dot, M is the name of the plane, not a point on the plane. Okay, some more vocab. Space is the set of all points. So everything you can see, length, width, height, and all the space in between. Collinear are points that lie on one line. So if I've got a line and I've got 2 points on that line, those would be collinear. Non-collinear are not on the same line. So A, B, and C are non-collinear because A and B lie on the same line, but C does not lie on that line with them. Coplanar are points that lie on the same plane. So if I were to box these in, all 3 of those coordinate points lie in the same plane. And non-coplanar are points that are not in the same plane. So you might see something like a flat surface in which you've got A, B, C, D, which would all be coplanar. And I might have a line or segment that passes through it and a point on there like E. So A, B, E would be non-coplanar. A, C, E would be non-coplanar. A segment is defined, or a line segment is defined as the endpoints from A to B and all the points between them. So a line segment ends, thus the words endpoint, right? And it would be all the points in between. Line segments can be measured. So lines can't be measured, planes can't be measured, but a line segment or segment can be. And you name this segment by just saying the 2 letters. So AB is a way to name this segment, or a segment symbol over the AB, or the word itself, segment. And rays. A ray starts at one endpoint and continues on unending in the other direction. So if I call this ray AB, or write it with the ray over the top, notice that A gets the endpoint and B gets the arrow, then this means the endpoint is A and it continues on in the direction of B, but it will pass through B and continue on without ending. This second example here would be ray BA because B has the end point and it continues on in the direction of A without ending. So you can either write it as ray BA or ray over the top of the BA where the end point's over the B and the arrow's over the A. Because these are unending, they also cannot be measured. Opposite rays are rays that share the same endpoint but point in opposite directions. Share the same endpoint, point in opposite directions. So in this diagram, if C lies on AB between A and B, which is the case, it's not necessarily equally distanced between them, but it is in between A and B, then CA would be opposite to CB. So ray CA and ray CB are opposite rays. And note that opposite rays form a line. One continuous line. Okay, so intersections. The word intersect means to meet, cut, or cut through. So multiple different types of figures can intersect. The intersection of 2 figures is the set of points in which are in both figures. So for example, if I were to cross 2 lines, their intersection would be a point. if I were to cross two planes, like in this diagram, their intersection would actually be a line. So different intersections look different. When you're looking at the diagram that's here, obviously this is a three-dimensional shape on a two-dimensional surface. So you've got to try to use your imagination sometimes. The dashes in the diagram indicate the parts that would be hidden from view. So if this was a solid piece of paper and then I cut it with slid in another piece of paper, you would no longer see this back part because it would be hidden. And that's what that dash is. You would also not be able to see part of that line because it would be hidden. So those dashes mean that they would be hidden from view. This vertical plane has B, that would be the name of it. And it has line K passing through it. So that would be the vertical plane. Point M also lies on that plane. Then you've got the horizontal plane, which we could call plane A, that's the name. Or because line PM or PQ or MQ lie on that plane, you could also call that plane PMQ. Again, those two planes meet at line K. All right, now let's do some application. This just says state whether it is true or false. Number 1, line PF ends at point P. Well, if it's a line with P and F, that means it is unending. So the trick word there is ends. It does not end at point P. This is false, and that is because lines don't end. Point S is on an infinite number of lines. So a single point can exist in any kind of line. If it was 2 points, it'd be only on one. But because it is a single point by itself, it lies on an infinite amount of lines, and that is true. 3, a plane has no thickness. That is also true. By definition, it has no thickness. 4, collinear points are coplanar. So if a line contains points, 3 points, then the plane that contains those lines is also going to contain those same points. So this is true. Planes have edges. Kind of a trick question. This is false. They look like they have edges when we use objects to represent them, but in fact, they don't end, so they don't have edges. 6, 2 planes intersect in a line segment. So remember those 2 planes that we had crossing before? They met at a line, but not a line segment. They met at just a line. So this would be false because of the word segment. 7 says 2 intersecting lines meet at exactly 1 point. 2 intersecting lines do meet at exactly 1 point. This is true. 8 points have no size. This is true. They have no thickness. They have no size. And 9, line XY can be noted as line XY with the arrows over both sides, and then YX with the arrows over both sides. And this is true. The order of the letters is not important when naming a line. Example 2 gives you the diagram, and then it says to use that diagram to classify if the statement is true or false. Number 1 says P is in M. And what this means is point P, because you can call it with just that single letter, is in plane M. Now the diagram is actually missing that point P, so there should be a dot next to P to distinguish the difference between N, which in your book would actually be a little bit bolder, and that would be the name of the plane, and M, again, would be a little bit bolder, and that would be the name of the plane. So that's how I know this means point P is in M. Point P is actually not on M. Point P would be on plane N, so this is false. 2 says B is in M, and B represents the line. That italicized B would be line B, and that is on plane M, so that's true. 3 says line YX contains B. So YX is this line here, contains P, sorry, and it does not contain P. P is not on that line, so this is a false. M contains line YX. M is the plane, that horizontal plane, and YX does lie on that plane, so this is true. A is on B, so that's point A on line B, and that is true. A and P are in M. A is in M, but P, we already said, was not in M, so this is false. And 7 says N contains P. N is that plane. Now it's the vertical plane. Contains P. P does lie on that plane, so this is true. That is the end of the notes for section 1, and we're going to move into section 2. Chapter 1, section 2 is called Measuring and Constructing Segments. So this is starting to work with line segments and how we measure them. So first up is using a number line. A coordinate is the number that corresponds to a point. So when you're looking at a number line, there's two things happening. One is the letters, and these are the names of the coordinates, and then the number value would be the actual coordinate. And then this slide also talks about distance. So distance can be found by finding the absolute value of the difference of the coordinates. So you can either, and there's a couple different ways to do it, you can either physically count from one coordinate to the other, or you can take the bigger number and subtract the smaller one from it, or you can just subtract and make sure it's in the absolute value so that it would, the order of what you're subtracting doesn't matter. For example, if I want to find the length of AD, A is -2 and D is 2. So I could count 1, 2, 3, 4. That's one way to get distance. I can make sure I do the bigger minus the smaller. So 2 minus a -2 would become 2 plus 2, which is 4. Or I can use the absolute value where order doesn't matter. So I could do -2 minus 2, but keep it in absolute value. And I'd get the absolute value of -4, which is 4. A postulate is something you're going to see a lot just in vocab terms, and a postulate is defined as a statement accepted without proof. So a postulate sometimes is pretty obvious. It's common sense. It's based on a definition or something that's easily determined. And the first one we're going to look at is called the ruler postulate. Some of them are very important. Ruler postulate's not something you're going to need the name of a lot, just the concept. But the ruler postulate says that the points on a line can be matched 1-to-1 with real numbers. So every point on a number line can get given a value. Once the coordinate system's been chosen in this way, the distance between the 2 points equals the absolute value of the difference of their coordinates, which is what we just used. So that what we just applied is actually the ruler postulate. A construction is defined as a geometric drawing that uses a limited set of tools, usually a compass and a straight edge. So we used to do these a lot in geometry. A compass looks like this, and you would use it by putting the point down on the paper, so the little point here, and then rotating around to make a perfect circle. So now in the digital age, we use our iPads or Notability, something like that, to make that perfect circle. We don't use these that often. And then a straight edge just being a ruler. The word congruent is defined as two objects that have the same size and shape. So if we're talking about congruent triangles, we're talking about two triangles that have the same size. If we're talking about segments that are congruent, it means they have the same length. So they have to be the same shape and size. Congruent line segments are segments with the same length. So if I measured this segment and then I measured this segment and they have the same length, then they would be congruent. It is a lot like equals. The symbol for congruence looks like this, and obviously the symbol for equals looks like this. Usually when you're doing congruent, you're talking about the object itself, and when you're doing equals, you're giving it a value. All right, this segment addition postulate is probably one of the more common postulates that we're going to use. And it says that if B is between A and C, then AB plus BC equals AC. Now, if you actually draw this out, logically, you already know this to be true. If I have a segment, A, C, and B is anywhere between them, it could be closer to A or closer to C or dead smack in the middle, it doesn't matter. Then if I took the length of AB and I took the length of BC and added them together, I would get AC. So that's all this says. AB plus BC would equal AC. And it works in both orders. If B is between AC, then AB plus BC equals AC. Or if AB plus BC equals AC, then B is between A and C. So you can use it in either direction. Example 1 says to plot these coordinate points and then determine whether the segments are congruent. So we're going to plot negative 3, 4, negative 3, 4 would be here, that's J. 2, 4, that's here, that's K. L is 1, 3, and M is 1, negative 2. And then we want to make the segments that connect J and K, and we want to make a segment that would connect L and M. Now these are vertical and horizontal, so we can simply just count 1, 2, 3, 4, 5, or from negative 3 to 2 would be 5. And then 1, 2, 3, 4, 5 from negative 2 to positive 3 would also be 5. The answer here is yes. JK would be congruent to LM. Example 2 says to fill in the blank with sometimes, always, or never. So in order for something to be always true, it has to be a definition or set in stone. Obviously, never is impossible, and sometimes means it can happen, but it doesn't have to. So number 1 says the length of a segment is blank negative. When you're talking about length, it's always absolute value, it's always positive, so it is never negative. Number 2 says if point S is between R and V, so if you want to picture it, R and V, S is somewhere in between, S blank lies on RV, and this is the segment addition postulate, so this is always. And 3, a coordinate can blank be paired with a point on the number line. This is that ruler postulate, and the answer is always. Example 3 says J is between I and K. So if you want to draw the visual, I and K are on the outside. J is somewhere between them. IJ is 2x. JK is 4x minus 6. And IK, which is the whole segment, is 30. So we're going to use the segment addition postulate to say that 2x plus 4x minus 6 would equal 30. 6x minus 6 would equal 30. 6x would equal 36 by adding that 6 to the other side. And then divide by 6, and x is 6. So our value of x is 6. To find ij, we're going to have to take what ij equals, which is 2x, plug in 6 in the place of the x, so it's 12. And to get jk, we're going to have to take 4x minus 6, plug the 6 in for the x, so it would be 4 times 6 minus 6, or 24 minus 6, which is 18. Okay, moving into section 3. 3 is midpoint and distance formulas. So things you should have seen before, but we're going to revisit them. The first is the midpoint. So the midpoint is defined as the point that divides the segment into two congruent segments. In this diagram, M is the midpoint of JK, or if M is the midpoint of JK, then JM equals MK, or JM is congruent to MK. So because M is the point that divides this into two equal segments, and I know that because of the 3 and the 3. I know M is the midpoint. So you would either see it with a value like that, you'll see it with tick marks, which match congruency marks, or it will say something like M is the midpoint of JK. A segment bisector is defined as a point, ray, line segment, or plane that intersects a segment at its midpoint. So it can only intersect a segment. A, B is the one getting bisected. It can only bisect a segment because it has to end, right? If it was a ray, you would never be able to find the center of it. If it was a line, you'd never be able to find the center of it. But a line segment, we find the point halfway between those endpoints, which is the midpoint. And either a point like M could be the segment bisector, or a ray, MC or MD, could have been the segment bisector, or a line segment, DC, could be the segment bisector of AB, or a line DC, could be the segment bisector of AB. Example 1 says, in the skateboard design, VW, so VW is the bisector. It bisects X, Y, so it cuts X, Y into two congruent parts at point T, and XT is 39.9, and it wants you to find XY. XY is the whole segment, so 39.9 is half of it. If I multiply 39.9 by 2, I get 79.8, which would be the segment XY. If it had asked for TY, it would be the 39.9. Obviously, it asked for the whole thing, which is why we doubled it. Example 2 says point M is the midpoint of VW. M is the midpoint, so it's cut into two congruent parts like this. Find the length of VM. So I want just one part here. In order to solve for X, though, I would set these two equal to each other. 4X minus 1 has to equal 3X plus 3. Subtract the 3X. X minus 1 would equal 3. Add the 1, and X equals 4. It's not asking for X, though. It's asking for VM, so I have to take that X and plug it in. 4 times 4 minus 1, or 16 minus 1, which is 15. Now, it actually wouldn't have mattered which one we plugged it into because they should be the same. If I plugged 4 in here, I'd get 12 plus 3, which is 15. Okay, midpoint formula is used when you're trying to find the midpoint of a segment that connects 2 points on the coordinate grid. And this is our midpoint formula. So if I have 2 points plotted on my coordinate plane and I want to find the point halfway between them, I add the two X values, divide by 2, and add the two Y values and divide by 2. This would equal an X of the midpoint and a Y of the midpoint. So it's going to be a coordinate point. Okay, so example 3 says the endpoints of RS are R1, -3, which is here, and S2, 4, which is here, and it wants you to find the coordinates of the midpoint. So we're going to add the two X's, 4 plus 1 divided by 2, and then we're going to add the two Y's, 2 plus a -3 divided by 2, and I'd get 5 over 2, -1 over 2. And you can rewrite that as 2 and 1/2 and -1/2, or you can keep it as 5 over 2 and -1/2. Both of these would be correct. Example 4 says the midpoint of JK is 2, 1. One endpoint is J, which is 1, 4. Find the coordinates of endpoint K. So this time, instead of knowing the two endpoints and looking for the midpoint, we have only one of the endpoints and the other midpoint. If x1 plus x2 divided by 2 gives me the x coordinate of the midpoint, and y1 plus y2 divided by 2 gives me the y coordinate of the midpoint, then from here I can plug in what I know. So I can make J the x1, y1, and I can make M the xm, ym. So x1 could be 1 plus, we don't know this one, so that would be our x2, divided by 2 equals 2, which is the x coordinate of my midpoint, and then y1, which is 4, plus y2, which is what we don't know, over 2 would equal the y coordinate of our midpoint, which is 1. So then to solve here, I can multiply by 2 on both sides. It will cancel from here. I get 1 plus x2 equals 4, and then subtract the 1, and x2 is 3. That's the x coordinate of the vertex, of the endpoint. And then on the right, multiply by 2. These cancel. 4 plus y2 equals 2. Subtract 4, and y2 equals negative 2. Okay, last thing in this section and for this video is the distance formula. The distance formula is used a lot in math. It will be used as you continue on beyond geometry, and it is used in a lot of standardized tests. So the distance formula, or the distance between 2 points, is the square root of x2 minus x1 squared plus y2 minus y1 squared. So this is if you're given 2 coordinate points. If I wanted to find the distance between A and B, I do the square root of x2 minus x1 squared plus y2 minus y1 squared. And it all comes from this right triangle that's formed here. You just really need to understand or know the formula, and then we'll just plug in those values. So example 5 is that. Find the distance between the 2 points. So I'm going to rewrite the formula at the top. Distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. This is my x1, y1. This is my x2, y2. And it doesn't matter which ones I make the ones and the twos. I could have reversed that as long as you're consistent within the actual coordinate point. So the square root of 7 minus 13 squared plus 10 minus 2 squared, square root of negative 6 squared plus 8 squared, square root of 36 plus 64, square root of 100, which is 10. So if you can simplify it, you need to, just like that. B, this is my x1, y1, x2, y2. So square root of x2, which is 4, minus x1, plus negative 1 minus 3. And I get the square root of 2 squared plus negative 4 squared, square root of 4 plus 16, which is square root 20. Now, square root 20 is not a perfect square. If it tells you to round this number, then you're actually going to plug that into the calculator and square root it. If it tells you to keep this answer exact, we're going to break it down. So I'm going to take that 20 and use the factor tree. 20 is 2 and 10, which is 2 and 5. And then for each duplicate or each pair of a number, one of those numbers is going to go to the outside. So it's 2 on the outside, and then the 5 would stay underneath the radical. The other way to break that down is to break it down into a product with a perfect square. So because 4 goes in here, I can break it down into 4 and 5, and the square root of 4 becomes 2, and the 5 stays underneath. So whichever way you're the most comfortable doing the simplifying your square roots, you want to stick to it. And again, you want to pay attention to directions. So if it says round it, then you're going to take the square root 20 and you're going to put it in the calculator, or you can approximate it, but you can put that in your calculator. And the square root of 20 is 4.472. So if it was 4.47, or if it said to round to the nearest tenth, it'd be 4.5, or it will say keep it exact, and your answer would be that 2 square root 5. All right, you made it through the first 3 sections of chapter 1. We'll continue in another video.